Hi, my name is Ravi, and I'll be talking about our work towards proactive, safe human-robot collaborations via data-efficient conditional behavior prediction. So first, let's talk about this idea of influence. So if this person is walking in isolation, they might take a straight line path. But if there's a robot in the scene, they might actually take a different trajectory entirely. So influence is the idea that these two trajectories, the person in isolation and the person around other agents, are actually different from each other. And specifically in this work, we think about a particular definition called conditional behavior prediction, where we want to understand how another agent acts as a function of our ego agent's future plan. So in HRI, we want to predict the future trajectory of the human probabilistically, conditioned on the past trajectories of the human and the robot, and specifically also conditioned on the future trajectory of the robot. So one question is, how might we get these CBP models? In general, people have looked, especially in the self-driving car literature, at training neural networks that can predict the actions of other agents conditioned on your ego agent's future plan using giant data sets like at Waymo and Uber. But in this work, we're actually interested in taking this big idea of conditional behavior prediction and bringing it to data sparse regimes like collaborative manufacturing and home robotics, where we don't have access to these kinds of large, diverse data sets for all the tasks we might be interested in. Specifically, we simplify this setting by thinking about CBP over goal states, because doing trajectory prediction over the full space of trajectories is actually very computationally difficult. And so our key insight is to separate the prior and posterior goal of the human into this theta h prior and theta h post here. And a lot of prior work has thought about this sort of observational goal prediction that's predicting theta h prior, where the robot is treated as an observer of the human, whereas our work thinks about conditional goal prediction, where we want to predict the future goal of the human conditioned on actually the past goal of the human and the robot's future goal that it wants to pick. And so our problem is situated in a 2D simulated manufacturing setting where the human state is in blue, the robot state is in red, and the possible goal states are here in green. So given an actual CBP model, we can think about utilizing it by trying to actively influence the human's goal. So naively on the left, the agent might choose this goal that's closest to it, but a robot with the CBP model might actually understand this influence and proactively choose the robot to influence the human's goal such that it can be more efficient. So here on the right, you can see at this point, the robot moves towards these goals on the left, and the human is influenced towards thinking that the best goal to choose is the closest goal to itself. On the other hand, the robot might want to stay out of the way of the human, which is what we call courtesy. Naively, the robot may influence the human to change goals, like we see in this left video, but a proactive robot can understand its influence on the person to stay out of their way and let them choose the goal that they wanted to initially. So in our work, we recognize that having an influence-aware prediction model gives us the freedom to choose the robot's objective automatically. So we specifically utilize a CBP model to switch between a courtesy and influence objective. Altogether, we call this our proactive controller. That also includes a probabilistic long-term safe control that outputs the robot's final action. And we also note that existing CBP approaches, like data-driven ones, assume that the robot's objective is fixed, so they just make the robot aware of how its low-level action affects the low-level action of the human, but doesn't actually automatically change its high-level goal like we're doing in this work. So in simulation, we compare our proactive model-based CBP method to a proactive learning-based CBP method that's based on existing models in the literature, as well as compared to a naive robot goal selection where you just choose the closest goal, and a reactive robot goal selection where you wait until you're sure what the human is going to do and then choose your goal in response. So on the metric of courtesy, we can see that both proactive models are very good at not changing the human's mind, which is what we wanted to do. And when thinking about efficiency, we can evaluate our models on different simulated humans, such as a stubborn human that never changes their goal, and an uncertain human that always waits until it knows what the robot wants to do before choosing its goal. And we can see that our proactive models are actually very flexible in interacting with both kinds of humans without any additional fine-tuning. So we wanted to see if this holds up with real people. So we ran an in-person user study with 21 participants that all interacted with the naive, reactive, and proactive controllers. And specifically, we don't use the learning-based controller because we don't have a pre-existing data set for this scenario. So here we can see an example of how a proactive robot might be helpful. For one particular user, they're not actually super sure what to do. So when the naive robot chooses the closest goal, they kind of try to choose the same goal and ultimately choose this far away goal. Similarly, with the reactive robot, the person takes a little bit of time at the beginning when they're hesitating, figuring out which goal to choose. But when interacting with the proactive robot, it sees that they're hesitating, chooses this far away goal, and ultimately, in the same amount of time, the two agents are able to be much more efficient. And we actually see this in our overall results. We can see that people tended to score worse and hesitate more when interacting with the reactive robot, whereas they were pretty good at interacting with the naive and proactive robots, which tells us that they're kind of okay being a follower to this naive robot, even if they're not super happy about it. And we can see in our next slide that when we ask people subjectively what they thought about these three different algorithms over a series of Likert scale questions, they tended to dislike the naive robot. So first we asked whether they thought the robot accounted for the goal they were picking. They thought the naive robot did not account for their goal, whereas the reactive and proactive robots did. And we asked if they thought that they changed their initial goal based on what the robot did. They thought that the naive robot did change their goals when the reactive and proactive robots did not. And finally, when asked to rank the three robots, 47% of participants ranked our proactive robot the number one choice. So in summary, we saw that model-based CVP enables proactive high-level goal selection. It can also perform very similarly to learning-based CVP in our simulations, and real users tended to prefer our proactive controller to our other baselines in real user studies.